All right, so next here's the converse of the angle bisector theorem. So we talked about not all converses are true, but in this case, in these last two cases, they've been true, right? So this is theorem 5-5 in the book. It says if a point in the interior of an angle is equidistant from the sides of the angle, then the point is on the angle bisector, right? So in other words, if we have an angle and we have a point on a line that's equidistant, right? So these are perpendicular and these are equal, then that means that the line that the point is on must be an angle bisector. Okay. So let's put these theorems into practice. So the first one, if M is on the perpendicular bisector of JL, then M is equidistant from, and so M is on the perpendicular bisector of JL, right? So here's JL. Okay, so M is on the perpendicular bisector, so this is the line that, okay, so it must be perpendicular and it must be a bisector. So then that means M is equidistant from the endpoints, right? So L and J. So point L and point J. All right. So yeah, so remember if a point is on a perpendicular bisector of a segment, then it must be equidistant from its endpoints, from the segment's endpoints. All right. So now it's if M is on the perpendicular bisector of JK. Okay, so we have JK here. Find a different color. And M is on the perpendicular bisector of it, so that means this is perpendicular. These are congruent. Then that means that what equals what? Well, there's a few things we could say here, right? But I think what they're getting at is we want these to be the same, right? Because it's equidistant from those points. And so JM, and since they have an equal sign, I'm just going to use the length, right? So without the segment symbol. So JM equals MK. All right, next, if M is equidistant from K and L, then M is on the, so if M is equidistant from K here and L here, right? So if those distances are the same, make a 5 here like that. All right, if those distances are the same, that means that that M must be on the perpendicular bisector, right? So that's the converse of the perpendicular bisector theorem. So M is on the perpendicular bisector of KL, right? All right, next one. If H is on the bisector of angle EFG, then H is equidistant from, so H is on the bisector of EFG, okay? So it means that these two are congruent. So that must mean that H is equidistant from EF and FG, right? Okay, from those segments. All right, and it doesn't look that way if you look at these lines, but those lines aren't perpendicular, right? Those are just going to, some points. So if we drew a perpendicular from here to here, then those would be the same, as long as H is on the bisector. All right, next one. If H is equidistant from EF, from FE and FG, then H is on the, So if H is equidistant from FE, this one here, and draw a better perpendicular bisector there, and FG, then H is on the bisector, right? Of EFG, right? Angle EFG. I just realized that I made a mistake on this last one. It's EGF was that one. So it's like this, EGF. And so if H is on the bisector of EGF, then H would be equidistant from FG is one of them, but then EG would be the other. So it should be EG right here, EG and FG. Sorry about that.